Very good day to everyone who's watching this video. My name is Hiran Raj, son of Ilango, with a matching number of 221401005 from the program Product Design with the code of UR6521004 from University Malaysia Perlis. And the reason I'm doing this presentation is to talk about a project with the title of Design Improvement and Analysis of Aircraft Engine Bracket for the subject of Computer Aided Engineering with the code of MMK21103. So, guys, without wasting any time, let us move on to the first slide. So, this is the first slide, which will be talking about the objectives of our project. So, let me read it out aloud. The first objective of this project, which is to create an efficient and lightweight design for the aircraft engine bracket that meets all structural and functional requirements. The second one is to determine the natural frequencies and mode shapes of the bracket to ensure it does not resonate with engine vibrations. And the third one is to evaluate the thermal performance of the bracket, especially if it's exposed to high temperatures during operations. So as you guys can see, this is the introduction for our project. So let us talk about the current situation. In the current situation, the aircraft engine bracket supports cowling during maintenance, and it is made up of titanium alloy, which is in high strength but costly and energy intensive. So our project goals is to explore alternative materials and also optimize bracket designs. So the evaluation methods used is CAE techniques, as I told you guys just now, the use of advanced computer aided engineering and linear static analysis to test ability to withstand static loads, and thermal stress analysis, which is to examine impact of temperature variations, and also free vibration analysis, or as known model analysis, which is to identify natural frequencies to prevent resonance. So SDG 12. SDG 12, responsible consumption and production, is one of the United Nations Sustainable Development Goals. It aims to ensure sustainable, efficient use of natural resources and to minimize the environmental impact of production and consumption processes. So, in the context of this project, SDG 12 is addressed by seeking to reduce the mass of the aircraft engine bracket through the use of alternative materials and thereby potentially lowering the energy consumption in the production process and contributing to more sustainable aviation industry. So that is the end of our introduction. So let us move on to the criteria of our design in this project. So this is the criteria that we have been provided by our lecturer for the designs of our for the designs and also the target specifications that should be reached at the end of our process. So the first one is we can use any metallic material other than titanium alloy must be considered as raw material for the bracket. For example, we can use aluminum alloy, we can use magnesium alloy, and much more, but we can't use titanium alloy as it is already uh, has been using in our current situation. So the second one is the bracket should support the weight of the cowling, which is 15,000 Newton, without presenting plastic deformation or fracture. And the third one, in redesigning the structure, the students must consider the mass, which should be lower than zero point 0.8 kilograms, achieve a factor of safety equal to or greater than 1.5, and a maximum deformation which is lower than or equal to 0.35 millimeters. So these are the target specs that we have been provided to obtain a good design for our engine bracket. And as you guys can see for the last sentence, the mesh should be set as tetrahedral element with a size of 3.0 mm, and the total number of mesh or element used in the analysis model must not exceed 120,000 elements. So let us move on to the design dimensions of our project. So this is the frame of the design and the dimensions of um, the engine bracket. We should follow all the dimensions that are given as you can see in the slide and design our bracket. My team is made up of three members, including myself, Diro, and also other two excellent teammates, which is Isa and also Hana. So, as you guys can see, the mass, factor of safety, and also the deflection for all three group members are that have been fulfilled the requirement that is needed, which is less than 0.8 kilos for the mass, and also above or equals to 1.5 for the FOS, and also less than or equals to 0.35 for the deflection. So for the mass, Hana was able to get the least out of out of three of us, which was 0.7086 kilograms. And for the factor of safety, me myself was able to get the highest um, among the three. And for the deflection or deformation, Isa was able to get the lowest, which is 0.8048. Therefore, let us move on to the next slide. So the final design that we all discussed and chose was Isa's design, um, because the main reason for this is, as you guys all know, she have successfully fulfilled all the requirements needed, and her design seems more neat compared to others. So that is the reason why we chose Isa's design, and also her deflection uh, rate is the lowest among all of us, which is 0.28048. So, as you guys know, as I told you guys just now, there are three methods for this project, which is linear static analysis, which has been conducted by Hana, and free vibration analysis, which has been conducted by me, and also thermal stress analysis, which has been conducted by Isa. So, the linear static analysis, as you guys can see, um, Isa's original design was quite high in mass, which was 2.05 kilograms, which did not meet the required mass, which was less than or equals to 0.8 kilograms. And the FOS was quite low, which was 1.1. And the deflection rate was quite a bit high than what was needed, which was 0.43 mm. And then after working on for several days, sleepless nights, she was able to finally get the present design, which was 0.78555 kilograms for the mass and 1.5367 for the FOS, and also 0.28048 for her deflection. So what we can talk about is the weight reduction. So as you guys know, the original bracket was 2.05 kilograms, and her present design was 0.78555 kilograms. Why? Significant weight savings are crucial for aerospace. And the factor of safety, original design was 1.1, which is inadequate, and the present design was 1.5367, which helps to improve in margin of safety. And for the displacement, um, the original design was 0.43 mm, and Aisha's design was 0.28048 mm. This is to achieve dimensional stability. So, this thermal stress analysis, the total deformation. The color concern indicates the deformation happens across the bracket with values that are measured in mm. The blue areas shows the least deformation with minimal value of 0 mm, indicating no deformation happens at that part. As the color shifts from blue to green, yellow, orange, and red, the deformation increases. The red areas indicate the highest deformation with a maximum value of 1.3723 mm. The maximum deformation occurs where the force part is applied. The other parts of the bracket remain relatively unaffected by thermal stress. So, for thermal stress analysis and for equivalent one measure stress, for color contour, the blue region is least stressed with a minimum value of 2.8065 megapascal, while the red region indicates the highest stress levels, reaching up to 4454.2 megapascal. As the color shifts from blue to green, yellow, orange, and red, the stress level increases. Same as the total deformation from the slide, from the previous slide. The maximum value took place at the fixed part, which is most likely to experience failure under thermal stress. The blue areas, where the minimal value took place, are less likely to experience thermal damage. And now we're going to talk about the FOS for thermal stress analysis. The color contours represent the different safety factors across the bracket. The blue region, which are maximum for which are for maximum value signify the highest safety factor and they are not at risk of failure. Meanwhile, the red regions which are for minimum value show the lowest safest safety factor and are at risk of failure. The maximum value for safety factor is 15 at the blue region while the minimum value for safety factor is approximately 0.0629 located at the red regions. The bracket shows the result that it is at high risk of failure under thermal conditions. So, for the free vibration analysis, um, the analysis shows the total deformation of the component at a specific natural frequency, which is 3.763.2 Hz. The color contour indicates the magnitude of the deformation with the color scale on the left correlating to the deformation values in millimeters mm. In this image, as you can see in the slide, the deformation ranges from 0 mm, which is blue, to a maximum of 109.58 mm, which is red. The red color indicates the maximum which occurs at the tip of the hole of the bracket. Since 3763.2 Hz is significantly higher than 275.8 Hz, there is no risk of resonance at this particular natural frequency. So this is for the mode 1 of free vibration analysis. So as you guys can see the table for this analysis, there are 6 different modes where the frequencies that has been written that has been shown on this slide. So all the frequencies are more than the natural frequency, which was 275.8. Therefore, there is no risk of resonance at this particular natural frequency. So guys, we're at the very end of our presentation, and the last slide is to be talking about the suggestions that can be taken into consideration to improve the design and also the analysis value, such as the total deformation, factor of safety, and also the mass of the design. So um, the main points are increase thickness, add fillets and chamfers, redistribute material, use stiffer materials, incorporate ribs or gussets, redesign load parts, improve boundary conditions, detail model analysis, and optimize design. So this all of these main points should take into consideration when you're designing your model, and hope that it will help to increase or improve the values of your analysis. So that's the end of my presentation. Thank you.